Okay, all right. Uh, what are we calling this? Okay, anyway, let me start the usual way. So, it's it's 25th of August, 2023, 1809 IST. I'm at Naisar Bhubaneswar. Naisar Bhubaneswar. Yamuna 401. All right. So, okay, what I'm doing here is a recap of my summer thing, summer work, if you call. So the point is, there have been events in my summer. Okay, so all right. Okay, for completeness, let me put the story straight. Okay, so what my academic interests are the following. You want to study physics, but in the language of mathematicians. In the language of mathematicians. Why? Because it has that subtle level of abstraction. Physics has that a fine flavor of physicality, and writing that fun physicality in terms of a rigorous and abstract mathematics is just too beautiful. In fact, you understand the deeper concepts of physics, right? Or you understand physics in a more deeper sense. You appreciate the problems theoretical physicists face and write them more rigorously. I mean, people don't get this. No, cancel. So, yeah, it might be obscure. Yeah, I really consider my academic interests are very obscure, just like many of my emotions are. But yeah, so that's it. So my interests are in mathematical physics. Mathematical physics. So basically, the studying the mathematics of the theoretical physics. Basically, yeah. I'm still an undergraduate. I might be interested in. I can be interested in things and just on a reading level, right? I'm still on a reading level. I have an whole year to explore this topic. I don't know what I'll do in fifth year, but yeah, I'll explore this topic for another year. So that should be fine. And yeah, so this summer finally, okay. These interests started developing since a year now. Like last time when I took graph theory, I slowly realized that computer science is not my go, but mathematics was really beautiful, explaining stuff. But graph theory was very discreet, and I didn't exactly match the vibe of it. But then I took the group theory in summer, and it was rather interesting, although I was not good at it. And then I just started loving math. That things have to be understood in a deeper sense. I mean, you see, if you go back to electromagnetism one, these course that I did along with graph theory in that semester, things were bad. I was way into a lot of abstract stuff, subtle stuff. They would just keep me up. Yeah, it felt like physics is not my thing on the levels of that, but physics is my thing, and mathematics is also my thing, and mathematical physics is the thing. At least for a more year now. Okay, I'll explore that nicely. So the last year, my interest started developing, and I started taking math electives like calculus of several variables, metric spaces, group theory, graph theory. These are all done. And then last semester, I took metric spaces. Yeah, calculus of several variables, metric spaces. Yep, and graph theory, group theory, and stuff. So it did give me a very good feeling of mathematics, actually. I mean, although I do understand that many basic concepts still uh, are still I don't know, still blurry, but yeah, I'm getting there. I mean, it's tough to do mathematical physics, like whole of the mathematics, whole of the physics I would be required to know, but yeah. But thing is, this field is interesting, and Okay. So yeah, this summer I finally plan to um, get there, right? Get there, start mathematical physics. So I thought I should focus on classical mechanics first, because obviously we're jumping into quantum mechanics, which is also based on a lot of subtle elements of classical mechanics. And so you just start with classical mechanics. That was my aim, and that requires a lot of mathematics. And I started with differential geometry. I I I started watching Friedrich Schiller's lectures on geometrical anatomy of theoretical physics. They were interesting, they were good, they were a very fine work of providing that intuition for a self study man. I mean, the person who's self studying by himself and stuff. It was very good. I wouldn't say it is completely rigorous, but did a very fine job of giving that abstract elements to you to discuss mathematics, to discuss physics. That is good, right? That is good. I cannot become a mathematician by myself, and it's a slow journey. And I learned some differential geometry, but I didn't play around much with it. I tried to soak in those definitions and feeling them. But a lot of that feeling comes from actually solving things. I didn't solve much problems, so that is something I should work on. So, and summer there were a lot of health issues I have faced, and I came back to campus. I had to go back to home for better health care and all that stuff. And then I came back to campus pretty late. I talked to my supervisor, kind of thing, and yeah, I worked for more. I worked a bit more on classical mechanics. I started classical mechanics after coming here in the last 2 weeks or a week of the summer vacation, and I started Taktajan. Taktajan is a very nice book. It just keeps me sane during the. I don't know. I love this book. I would keep this book with me, and yeah, this is just too good. So I started reading there, but it's only been few topics. Hospital shiftings. I've been sick. A lot of things happened. Taking care of myself with respect to health more and stuff. And finally, here I am. I need to submit a report by 31st of August, which I'm okay with. I just need to meet with my supervisor again to. Supervisor? Guide? Yeah, guide. What the hell? Okay, guide. It's not a very serious thing. I just went to them and just told ki I want to do this and stuff, and yep. So so I did some work in the last few weeks of summer related to physics, and that's what I'm going to write in my report. I already wrote a lot of it. I developed some mathematics. Developed in the sense, yeah, I wrote some mathematics that I learned required for that few initial topics in physics, and that's what I'm going to revise now and write a bit of part, like basically the principle of least action. I haven't written it in my report yet, and that's what I will be discussing with myself now, and I'll write it soon today, and hopefully I'll finish it today up to wherever I think I should be doing. And it's nowhere complete summer project. I want to continue this direction till an year, maybe reach quantum mechanics eventually. I'll see. Prerequisites are hefty, defty fucking things. Very interesting things. I'll slowly get there. Okay. That was the premise of things. Okay. Now we'll set up the grounds. So of course, as I started reading Taktajan, he starts with saying a point particle is a. Well, classical mechanics describes systems of finitely many interacting particles, and it is closed if it does not interact with outside material bodies. And so basically, a particle state lives on a n-dimensional manifold that physicists call configuration space in their lingo. and it has it has a dimension n, so there are n coordinates that could be then n generalized coordinates when you take a local map from the manifold to the Rn, the dimension of the manifold, and this dimension n is called the degrees of freedom. And again, physicists lingo, very very intuitive things, and then you call q dot I mean qi's are the generalized coordinates and q dot I are generalized velocities. Okay. And interestingly, these q dot I are bases of q dot I's are bases of You're right, I's are actually a basis of in the tangent space and stuff. So and this nature makes these coordinates depend on makes this double derivative of these coordinates double derivative with respect to time depend on these generalized coordinates, such that it gives us an equation of motion. Now this physicists, mathematicians try to put it in a rigorous language, and that's what I'm going to do right now. So the nature gives us the differential equations of q with respect to time, and then it's already give us the equation of motion that explains its motion, basically. So how do we do that? Okay, so you have a Lagrangian system M, L, where M is your configuration space in n-dimensional manifold and smooth manifold, and L is called Lagrangian function, or simply Lagrangian, that takes Tm cross R. You see, this Tm is a tangent bundle. It's a set of all tangent spaces. And its coordinates are represented by q, q dot. Basically. And this is basically your time axis, and this is taken to another real thing in a real line. Okay, so your Lagrangian functions takes tangent material cross R to R again, and the motion of this Lagrangian system is described by the principle of least action. Now we'll formally set up the principle of least action. Okay, for that we consider the space of all the smooth parametrized paths in M, the configuration space from point Q0 to Q1 in time T0 to T1, right? That means, let me draw a picture for notations, some bit of notations here. It's gamma T0, T1 to M1, such that gamma T0 is Q0 and gamma T1 is Q1. Alright, you see, basically it's Q0 here, Q0 1, this is your m-dimensional manifold, and you have paths, smooth parametrized paths connecting these all sorts of wobbly things, and each path is an element of this space. This space is interestingly an infinite dimensional Frechet manifold, in fact a real Frechet manifold. I'm not sure what Frechet manifold means, but it's analog to Rn. I mean, M being locally homomorphic to Rn, instead of Rn you put a Frechet space. What is a Frechet space? I don't know. It's something. I'm not sure about that, but we don't use that for now. So here is your space. It's a real Freshy manifold. These set of paths from Q0 to Q1. It's actually a T0. It's actually a T1. And if you consider this space of paths, it gives us an interesting space to deal with now. How? Let's see. The tangent space of this at gamma. Gamma is it's a right. Okay, maybe there is some specific gamma. This gamma belongs to P of M. Q0 T0, Q1 T1. Right. This T of gamma T gamma P of M is a tangent space at gamma. It consists all smooth vector fields, like sections basically. Smooth sections along. Okay, Taktatin says they are all smooth vector fields along the path gamma in M, which vanish at the endpoints Q0 and Q1. So T gamma of PM, it's a space of it's a tangent space to this gamma, right? So it's basically set of all those elements which are basically smooth sections. Like Q1 पे tangent ले लो, right? Q1 पे tangent ले लो. You see, if you think in terms of P of M, all these elements are this way, right? So if you take tangent on this point, you get a zero. Basically, a zero vector. If you think of in terms of M now, this Q0 is being taken to a zero, belongs to T of M, and this is Q1 also takes to. But this whole thing is if iska tangent space lega, so it's like your vectors, your tangents to every points, right? Smooth vector fields, मतलब basically जो M से TM तक लेके जाएगा, TM से पाई लेके जाता है, TM to M. This whole is a tangent bundle thing, tangent bundle lingo. Okay, so that's the intuition there. And now you are saying that no, what are you aiming for? You are aiming for a principle of least action, you remember? So if you have paths from Q0 to Q1 and all sorts of thing, now you consider a variation of this, a variation of a specific gamma. You consider the variations of this, smooth variations with fixed ends, right? Smooth variations with fixed ends, right? So this is called gamma, right? Yep. So gamma M is a smooth path in P of M. It's yes, right? Yeah, it's smooth path in P of M. It moves from one trajectory to other trajectory smoothly, passing through gamma, right? Right. Okay, a smooth path. This is called a variation with fixed ends. Variation with fixed ends of path gamma T belongs to M. Okay, of path gamma T belongs to M. A path is simply a real number to M map, here being your time axis physically and stuff. Let me check the mic is on or not. It happens, man. It's interesting how almost 2 years ago I was recording diffraction integrals and I realized I didn't turn off my mic, and ever since I'm very conscious about whether I'm turning on the mic or not. It's interesting. I mean, one event can actually change things, right? You start valuing about things and you start becoming careful about things. So yeah, I really value these recordings for that. Yep, sure. Yeah, they're not just something that just go lost in the internet. It's something I value close. I keep them close and I keep looking at them, feel good and stuff. So gamma of m, this is gamma. Gamma of m is a variation with fixed endpoint ends of path. That now a variation, this gamma is actually a family. Okay, like this can be parameterized as a family, okay, of paths in M, right? This is basically a variation with fixed ends of gamma t. It can be seen as paths. It can be seen as a family of paths in M parameterized by epsilon. Okay, parameterized by epsilon. It is very straightforward, right? Minus epsilon comma epsilon naught to M, which of course needs explanation that sigma gamma t of 0 is actually gamma t. Like if you put 0 in the terms of this family parameter, you get the original trajectory for t naught less than or equal to t less than or equal to t1. And then you should also mention that no matter where you go at t naught, you will remain at gamma of t naught, okay, which is basically q naught. And gamma of two gammas, that's fine. T1 comma epsilon will be gamma of T1 is actually Q1. Okay. That's fine. That's totally fine, right? Yes, cool. Now the tangent vector delta gamma, you denote this by delta gamma. You write this as del gamma by epsilon equals to 0 belongs to T gamma PFM. So it's basically this gamma belongs to T gamma P of M, and where these families of parameterized curves are there. Iska tangent lena is basically, okay, you have a function of points and you define this gamma ka derivative, the tangent vector, specifically this iska as gamma ka derivative at epsilon 0, right? This makes sense. Okay. Sanity check. What is gamma here? It's basically an R cross R map to P of M. Is it? It's not exactly that. It's actually M itself, but yeah, chalega. When you consider this gamma T. Okay, all right. It's actually M. It's actually M. Yeah. And this M, you say, yeah, exactly. And this M, that such maps belongs to P of M, right? Yeah, that's true. That's consistent. That's mathematically consistent and rigorous and good enough. Now this derivative is what? This derivative is of gamma, of specifically the gamma belongs to P of M. So can we take such derivative? Derivative is basically the tangent vector, right? Tangent vector of gamma, right? Basically gamma belongs to P of M, right? So basically what we are doing is tangent vector at this point. That's it. What? Really? That's the notation, but for more pedantic description, let me refer to my report. how do you write a tangent vector at a point P in your manifold? It's not exactly point P, it's passing through a curve. You have to mention a curve. Okay. Sure. Okay, let me just refer to my work here, which is overleaf. Okay, we'll compile. Alright. Okay, this exactly. So what is your tangent vector? It takes okay. So basically, a tangent vector of any point in a manifold takes a function. It's a function of which is from a manifold to a real number. Actually, it eats up that function, right? So then you can define a nice little derivative, nice little funny derivative. Yeah, basically smooth functions from M to R. That's what it eats. A tangent vector eats. So now one does when you say del gamma by del epsilon, what do you mean? Okay, I actually figured this out, but okay. This is, of course, this is just a notation. Nothing fancy is inside. So basically, explicitly, if you write, this is the definition. It's a pullback. It's a pullback? What am I talking? I don't know. Let's see. It's a push. What the fuck? Wait. So basically, we have okay. We have a push forward map. Yep. We got a push forward map from TPM to no. Do we? Yeah, we have a push forward map from the hell. Okay, so Okay, so okay, I have some other notes which are helpful for this thing. Let's see. Okay, so yep, I found this notes. I forgot, but I'll sure get them again. But okay, yeah. So this says okay. So it's basically we want to define a derivative of this gamma at epsilon 0. Okay, so how do you define it? So how do you define it? Well, takes a point r to m function from okay, so basically a tangent vector of tangent vector t gamma p of m is tangent vector belonging to t gamma of pm actually takes what happens, a c infinity of p of m and turns it to a real number. That's the plan of this. What is the c infinity of p of m? What is p of m? It's actually an r to m map. That's the tangent vector. But what is c infinity of pm? C infinity of pm is pm to r maps, all the continuous pm to r maps. What is p of m actually? Pm is r to m maps. Okay, something's wrong. Force of push forward from where to where? It's a push forward from T of gamma PM to T of gamma T of M. Right? You have this family of this is a So essentially you can see gamma T0 comma T1 as a T0 comma T1 to M. Now this belongs to P of M, of course, but this gamma epsilon, so you can write gamma epsilon as epsilon, right, gamma of T, something like that. Epsilon naught comma epsilon to where? To M, right? But this is a function of, this function is a function of epsilon naught, right? Fair enough. So now you take this thing, a push forward to M at T0. This belongs to T gamma of Tm. This is delta of gamma T. You have the push forward defining definition. Cool. Now you consider a tangential left. For example, that is gamma T01 to Tm is the path. Tangential left to this path is gamma prime T0 comma T1 to Tm, defined by the push forward as gamma star of del by del T. Alright, that's simple. And now you start your definition. Okay, now this now the insides are like this of course belongs to the tangential vector to T0 comma T1. That's fine. In other words, gamma prime T is the velocity vector. The velocity vector of a path gamma of T at time T. Now you have the usual definitions. Definition string starts, which says essentially that your actional functional is actually a map from P of M to R. That's how Takhtajan writes. P of M to R. That the space of functions, the space of trajectories, fixed trajectories to R of a Lagrangian system ML is defined by S of gamma is T0 to T1 L of gamma prime T comma T. Now you see this gamma जो था वो M में था gamma. Now when you consider tangential left to this, it actually goes to gamma prime, which actually has two coordinates, right? It has q1 dot qn and q1 dot qn dot. I mean, it's actually a notation. It's not a time derivative. It's not a time derivative. These are called standard coordinates on the tangent bundle, which we'll get soon. We'll get to soon. I mean, we already got there, but yeah. Okay. Now this Lagrangian is now as a function of Tm. Basically Tm था ना. Tm. Oh yeah, it is nice, right? It's L. Tm में कुछ coordinate, comma time में कुछ coordinate था, which is R. Now Tm में you have the gamma prime T, and now it's Lt. That's fairly consistent. Now it's T0 to T1 L of gamma prime of T comma T dt is the action functional. Okay, now the principle of least action says, see, the point is with these definitions there is no vagueness. right? It's straight up definitions. I mean, it you don't have to think philosophically at every point. That's the thing, right? When I started reading EM1, for example, one of year back, it felt very weird. I was like doing a lot of thinking, abstract thinking between stuff. It was not so good for theoretical physics. You just have to do hard and fast things and move on. I mean, of course, there's a lot of critical thinking involved and a lot of physicality. That's not what I'm talking about at this point. Yeah. Now, the Hamilton's principle, or the principle of least action, says a path gamma belongs to P of M, Pm, describes the motion of Lagrangian system ML between position Q0 belongs to M at time T0 and Q1 belongs to M at time T1 if and only if it is a critical point of action functional S. That is, T by D epsilon equals to 0. S of gamma epsilon is actually 0. What now? Where gamma epsilon are the variations of gamma t. Now we have considered a large set of things where the endpoints need not be, endpoints are fixed here, but you took all the space of functions. You can restrict directly to the family of functions, which is, I would say, it's too much, right? It's fine to consider P of M and stuff. Okay, so that's the thing. It's gamma extremizes the action function. Fair enough. Now the critical points of action functions are called extremals, and the principle of least action states that the Lagrangian system ML moves along the extremals. The extremals are characterized by equations of motion, a system of second order differential equations in local coordinates on Tm. Now this is interesting. What we define is this. Now we'll get to the interesting part, that we can actually get an interesting equation out of this. Right? But before that, we can do a quick revision of tangent bundle mein coordinates. They're called standard coordinates, where you basically define fiber corresponding to the coordinates in the fiber corresponding to the bases d T1 are called as standard coordinates. Okay, so basically, where V1 to Vn are coordinates in the fiber corresponding to the basis arm. What's the fiber? Fiber is from M to TQM, no? Yeah, our coordinates in the fiber exactly corresponding to the basis DQ. Acha, basically that's it. Yep, the basis coefficients are read as standard coordinates here. Standard coordinates are Cartesian coordinates on star. Okay, you push forward to Rn, U to R. Okay, obviously. you have a homeomorphism from U to Rn, and you take a push forward from U to Rn, and Ht of Rn is actually, yeah, you could say that, because straightforward tangent space of Rn is Rn, and Rn cross Rn, and have the property. Yeah, you see, bundles have this very close. Bundles are generalization of product manifolds, right? That's a very nice abstraction, and I would like to do many examples on that, but not now. Okay, and I have derived the, if you consider like two different charts, they have having their own transition functions, and see when the locally, when you take a chart, of course these are defined locally, right? These coordinates are defined locally. Now when you go to local coordinates to another chart, tu1, tu prime, these are transformed by actually a matrix which I have derived in my report, it was simple, actually, rather simple definition. Consider two charts u, x and u prime, y of smooth manifold line such that P belongs, and we have a vector x in the coordinate system y as supreme coordinate system as xi, let xi, writing dy as we have xj is transmission magnetism and general transmission. The tangential lift of a path in standard coordinates is oh, acha. Like generally the standard coordinates in TU or TM is just Q1, Q1 and Q dot 1. Okay, acha, fine. Okay. Okay, that's fine, because Okay, my doubt is why was the coordinates on TU were written as Q dot 1 T. Okay, that's just okay, but point is V1 of, I mean, they're still pretty much, how are they still velocities now? So what are QI? Gamma T of M to M to R करने वाला क्या है? उस पे act करेगा ना velocity by default they're not mean anything. What does this mean? What does this mean is Q1 of T is basically a map from itself from M to R, no? Or no. So basically it's derivative of that. Oh, I see. It's the derivative of that. So that's called time derivative. Okay, that is now clear. Time heals, time learns, time. Okay, that's great. Since we only considered paths in TM that are tangential lifts of paths in M, there will be no confusion. The reserve notation Q of T for general paths in TM. अच्छा समझ रहे हैं ना ये. अच्छा ठीक है, ये गामा करस्पॉन्डिंग ही नहीं हो सकता है ना. जनरल पाथ्स इन टीएम. ठीक है, इसको थोड़ा और भी देखना पड़ेगा, मे भी लिखते वक्त थोड़ा क्लैरिफाई हो जाएगा. बट पॉइंट इज़ कि वही टीएम पे जनरली क्यू ऑफ टी वी ऑफ टी लिखते हैं, बट टेंजेंशियल लिफ्ट कंसिडर करते हैं. मतलब गामा ऑफ टी क्यू है, फिर क्यू से आर जाता है, क्यू डॉट इधर जोड़ देते हैं. दिस इज़ बेसिकली गामा प्राइम टी देगा, बिकॉज that's how it was defined. I mean, I'm getting the game slowly, not completely I would say, but I'm getting the hang of it. Maybe when I'm writing it will be clearer. And now it's for the big boy theorem, which is called the Euler-Lagrange equation. It uses Euler-Lagrange equation. The equations of motions of a Lagrangian system M, L and standard coordinates on Tm are given by Euler-Lagrange equations. The equations of motion of Lagrangian system in standard coordinates on Tm, basically q dot, are given by Euler-Lagrange equations, which is dl by dq q dot t minus d by dt del L by del Q dot Q dot T equals 0. Suppose first that an extremal gamma T lies in a coordinate chart U of M. Standard coordinates using integrations gives right. Chalo. Then a simple commutation gives d by d epsilon of epsilon equals 0 s of gamma epsilon implies d by d epsilon equals 0 t naught to t1 L of q of t comma epsilon q dot of t comma epsilon comma t dt. Write I equals to 1 to n t naught to t1 del L by del qi delta qi plus del L by del qi delta qi dt equals summation I equals to 1 to n t naught to t1 del L by del qi minus d by dt of del L by del q dot I delta qi dt plus summation I equals to 1 to n del L by del q dot delta qi just t naught to 0 the second sum is the last one additional property. The first sum is 0 for arbitrary smooth functions. So very careful carefully keeping things okay. Okay. somehow okay. First one 0 for arbitrary smooth function with the transition at the endpoint. This implies that for each term in the sum integrand the integrand is identically 0. Acha. Yeah, अच्छा लगा मुझे क्योंकि mentioning that delta q is actually arbitrary is important. Delta q was arbitrary was an important factor of decoupling the summations into. Okay, fair enough. Since now comes an very important thing. Since the restriction of an extremal of action functional S to a coordinate chart on M is again an extremal. Since the restriction of an extremal of action functional S to a coordinate chart on M is an extremal, each extremal in standard coordinates on Tm satisfies Euler-Lagrange equations. to function is just put in to संतुष्टि दाना संतुष्टि दाना संतुष्टि दाना संतुष्टि दाना
Of drinking raw milk, and one thing you might not know is that cows also get tuberculosis, and they can give it to us. Vegas is a bit more by a woman named Gloria Paris who contracted tuberculosis in her bones from drinking raw milk. She endured countless surgeries, horrific pain, years of hospitalization, and this isn't like ancient history. She's still...
okay. The Gator derivative, the result of the above computation when gamma lies in coordinate champion can be written as this.